Welcome, everybody. I think we're going to go ahead and get started. My name is Erin Hester, and I'm an associate professor in civil and environmental engineering at UC Merced, and I'm the associate director of Citrus at UC Merced. I'd like to welcome you all to the 13th year of the Citrus Research Exchange Seminar Series and 21 years of the Citrus organization. We've hosted a remarkable lineup of technology innovators in person at Siddhartha Hall and are glad to see all of you joining us virtually today for the Fall 2021 series. I'd like to give a special shout out to the UC Merced Live Watch Party happening at the UC Merced campus, and I encourage you all to contribute both virtually as well. Today, we are going to be joined by Shijia Pan. Dr. Shijia Pan is an assistant professor at the University of California Merced. She received her bachelor's degree in computer science from the University of Science and Technology of China and her Ph.D. degree in electrical and computing engineering at Carnegie Mellon University. Her research interests span cyber physical systems, Internet of Things, and ubiquitous computing. She's worked in multiple disciplines and focuses on indoor human information acquisition through ambient sensing. She is the recipient of numerous awards, including the Rising Stars Award in EECS, the Nick G. Vlahakis Graduate Fellowship, the Google Anita Borg Scholarship, and numerous awards for best papers, best posters, best demonstrations, best presentation, and audience choice awards from various ACM and IEEE conferences. It is my great honor to welcome Professor Pan. Thank you.
Thank you so much for the introduction, Erin. Let me share my screen here. Is the screen sharing okay? Yeah, good. So hello, everyone. My name is Shijia, and I'm an assistant professor at UC Merced. So I have been working on physical vibration-based human sensing, and I'm very excited to share some thoughts and our progress on this topic here. So the work I want to introduce today, I summarize it as a sense for less, where we utilize the physical knowledge to adapt the cyber-physical system and reduce the resource required for occupant monitoring. So with the rapid development of the information technology, various cyber-physical sensing systems have been designed to capture human information, and that enables various smart building applications such as smart home, smart healthcare, smart elderly care, autonomous retail, etc. And when we say human information, that's actually quite a broad term. And the scope for this talk here is focused on the physical measurement of the people, where we want to know the identity, location, activity, and the various physical condition of people, such as gait balance or other type of information for the indoor occupants. And of course, we are not the first one trying to do this at all. So various sensing modality has been explored to achieve this occupant monitoring, including both device-based and the device-free systems. So for device-based system, they would rely on the user to carry a device with specific sensors on it. It could be your smartphone with IMU, microphone, camera, etc., or wearables with optical sensor to measure a heart rate, wearable EEG, and immersing technology on earables, which enables fine-grained sensing for various biometric measurements. On the other hand, the device-free system often rely on fixed infrastructure sensors in the environment. That is to say, the person does not need to carry the device, hence we call it device-free. And a few examples we'd like to mention here, including vision-based method, passive RF, Wi-Fi, for example, light-based sensing. They rely on their measurable phenomenon that's induced by human and environment, enable either direct or indirect human sensing. So we focus on an alternative modality of human sensing where we monitor human-induced physical vibration to infer the target information. So people actually cause vibration all the time, and we rely on a variety of vibration sensors, both device-free and device-based, to capture the human-induced physical vibration in a passive way. And the captured vibration signal is processed, and then we can model or learn the human information from it. And a few advantages of the vibration-based human sensing, including the following. So because the vibration propagates, it will allow us to sense the target information from a distance. Hence, we can do a sparse deployment and observe remotely. Unlike vision or speech, this type of information contained in the vibration is not directly interpretable to people. And as a result, it has to be indirectly inferred. And this actually makes it less intrusive in terms of perceived privacy. And since people are causing vibration all the time, it will allow us to continuously monitor people over different scale with different information resolution. So for example, at the room level, when you walk, cook, type, or even sleep, your body would move and interact with the object in the room, and hence induce a vibration. So these vibration actually contains information of your activity, physical condition, and even behavior. So in fact, we start this line of research, which we refer to as structure as sensors for indoor occupant monitoring, after we accidentally sense people not washing their hands after using toilet during one of our experiments near a restroom. So if we zoom into a person level, your heartbeat, your breath, muscle activation also induce vibration. Although this vibration may be at a very different scale comparing to the room level vibration and contains different type of information. And we design different forms of factor of sensors to capture these vibrations. For example, let's further zoom into the body part level, say the mandible or what we call our lower jaw. The vibration generated during the everyday usage contains more indirect information there, such as your teeth condition or unvoiced speech. So people say a video is worth 1,000 pictures. So here we demonstrate the intuition of a vibration-based human sensing with an example of a pedestrian walking by a floor vibration sensor. So we place a geophone sensor, which measures the vibration of a surface on the floor in the hallway. And then we ask a pedestrian to walk by. So we can see that when the foot falls on the floor, each foot strike would induce an impulsive wave. And this wave would propagate through the surface of the floor and then can be captured by the geophone sensor. And our event detection algorithm will be able to extract this vibration signal. And you can see we mark them in the red box on the signal that's showing on the left corner in the video. And because each person has a unique walking pattern, which we call gait, their footfall-induced floor vibration vary, and that's unique to each person. Then we can actually extract the features from this marked signal and train a classifier, then be able to identify people when they walk by the sensor. That's how we extract the human information and achieve the occupant monitoring. And we are actually actually achieved up to 99% accuracy over 10 people. So other than the pedestrian identification, we have been exploring a variety of applications with our collaborators all over the world, including and not limited to nursing home, where we want to understand the condition of the elderly, their gait, their walking balance. We work with a sleep lab, where we try to understand the sleep quality of their children patients. We also work with our local dental office, where we want to understand how people use their teeth and whether we can learn about their teeth oral health. In addition, we put our vibration sensing system in a pig farm in Thailand, where we are learning the piglets' activity and whether they have health issue as well. So we published a bunch of papers on different type of human-animal information acquisition as listed below, including the occupant identity, location, gait balance, activity recognition, etc. So while we're still continuing exploring new applications with vibration sensing, we also look into the gap between these research deployments and the long-term large-scale monitoring. So this gap we're trying to fill here is, can we reduce the resource the system needs to make the system truly pervasive while acquiring more information? By resource, I mean, say, number of sensors, the deploying efforts, and the data labeling efforts, which we'll cover in the rest of the talk. So the first challenge I would like to discuss here is, how can we use less sensors to acquire more information? So by less sensor, what I mean is, say, for in-home long-term monitoring, it's important to reduce the number of sensors for the non-intrusive design. We actually need to do this for multiple reasons, such as we want to reduce the perceived privacy intrusion, the cost, maintenance effort, and to reduce the system impact on the person. By more information, I mean for many emerging applications such as mental or behavior profiling, or fall risk prediction, the fine-grained continuous monitoring is required, and we need to infer with very high accuracy. So despite the fact we said earlier that vibration propagates, and that gives us the advantage of sparse sensing, many factors in real life would actually impact this advantage, such as your floor material or structure elements such as a beam underneath your floor, or loads in the environment such as furniture. And all these factors may in turn impact the system performance. So of course, we can have a very simple solution here to avoid all this real world impact. So let's just put sensor everywhere. However, unfortunately, I'm not that rich and cannot just burn funding like that, right? So this, in addition, this also defeats the purpose of using vibration sensing in the first place to enable sparse deployment. So we have to look for other solutions. And we have another very simple solution here, is that we can characterize these factors by experts. You can see here we have an example where a Ph.D. student is characterizing the deployment using a hammer knocking on the marked location on the floor. So then empirically, they can provide recommendation accordingly to ensure that the system gets good data. However, this type of characterization is still costly and very difficult to scale. I cannot just send a PhD student all over the world just doing this. So can we characterize the deployment without this manual effort. So on the other hand, when we put the sensor in the deployment, we are already capturing human-induced vibration, right? So can we just repurpose it for the deployment characterization? Since people are moving around in the sensing area, it means that the vibration we induce not only include the human information, it also includes the deployment information as well. So taking the footstep induced flow vibration when a person walks by a sensor, as you see before in that video, what we can learn from this type of signal about the deployment itself is actually a lot. So for example, here we actually can calculate the attenuation model of the floor and understand the target signal strength. We can also infer the homogeneity of the floor material, and we can extract the frequency domain characteristics, like the fundamental frequency of the structure or structural modes excited by the target excitation. So based on the heuristic estimation of these footfalls, the spatial temporal information of where you step, we can actually calculate the parameters of the physics model describing all these deployment properties. So now we have these deployment properties that can be modeled from the sensing data we acquired. Can we further improve the system performance? For example, putting sensor at a location where the system performs the best. So we formed this optimal sensor location selection problem as a multi-armed bandit problem, where the multi-armed bandit problem describes a scenario. There are multiple slot machines on the one-armed bandit, and a gambler that can take action to pull their arms one at a time. So instead of looking at a slot machine that gives you the best reward, we are looking for a sensor location that gives you the best system performance here. So for example, at a given deployment, the system can recommend, say, multiple sensor locations that you can put your sensor, which we marked out here as colored cylinders in the layout. So these sensor locations, they might have different uncertainty of the system performance. And then we can use the Thompson sampling to learn the model on the sensor locations feature, which is the deployment properties we just measured or modeled with the human information, human-induced signal earlier. Then at every timestamp, the system will acquire the user feedback, say how accurate is the system over this period of time. And then at the end of this time step, we can recommend a new location to put the sensor. So due to time limit, I'm going to skip a lot of technical detail here. And we do have a few publications on this where you can find them if you're interested. So we evaluate how our system learns the optimal sensor location over time with application of pedestrian identification with floor vibration. Here we collect the data from 7 different environments. We use 5 for training, 2 for testing. So each environment, the system will be able to recommend over 4 sensor location options. And we measure in total 5 deployment properties as a feature by repurposing the human-induced vibrations data as we explained slightly earlier when the occupants are walking in the sensing area. So we compare our system using Thompson sampling to the MAB with random sampling and evaluate the recall rate at K. That is to say, whether we successfully select the optimal sensor location in the top K recommendation. So we took the online training with the data from the 5 knowing environment, did the offline testing on the 2 unknown environment. The feature here shows the optimal sensor selection recall rate with only 20 time steps for training. The x-axis is a k varying from 1 to 3, and the y-axis is a recall rate at k. So our system achieves an up to 2 times improvement comparing to the baseline method and achieved over 90% recall rate at 3. So the takeaway message here is that by learning the physical knowledge of the deployment property from the ambient human sensing data, we were able to adapt the system to achieve better performance. And in summary, we leverage the physical knowledge to optimize the system so that we can use limited or less sensors to get more accurate information. So we published a couple of papers on this topic, including the configuration optimization, sensing quality assessment, sensor placement optimization, and the sensing unfairness analysis based on the social economic bias. So great, now we can sense with less sensors. Seems that we solved the problem. So let's take a look at what's behind the scene. So another secret ingredient of a successful sensing system is our hardworking graduate students who spend a large amount of time to install or configure the system in the first place. So the second challenge that we are trying to target here is how can we reduce the configuration efforts by sensing and adapting the system itself. So the reason we want to do this are twofold. For some application, the system needs a sensor's physical information to conduct the collaborative computing. And for most of our application that we are targeting in-home long-term occupant monitoring, especially for large-scale deployment over residential buildings. This information or configuration is unique for each deployment. So it's going to be difficult, if not impossible, to rely on experts like our graduate student to conduct the installation and configuration in a large scale. So if you ever install a smart home device, either a smart switch or a smart light bulb or a surveillance camera, you might ask why this is even a problem. Just plug it in, right? So for example, this exact camera view that you can see here can capture pretty good information from room 101 to 102 to until 108 and capture it pretty well. So simple, just put it there, right? So let's take a look at our favorite vibration signal again. The floor vibration signal when a person walks by a sensor. So can you tell which sensor in the hallway that marking blue circles does this signal belongs to? Or by looking at the signal, can you tell me where is the sensor placed in this hallway? So the problem here is that because the vibration sensing, we are indirectly inferring the information from the sensing signal. The signal itself is not directly interpretable for human, which just like we said before, it's a great thing because it will help preserve the perceived privacy. But just like a lot of things in your life, everything is a double-edged sword, right? So it also leads to the lack of association to physical world. That makes the configuration very difficult. So especially for applications that require the sensor say absolute location in the room, say for example, for multilateration-based localization, gate parameter measurement, gate balance monitoring, they all need the system need to know the sensor's absolute location. And manually input this information is just impractical for an end user and difficult to scale if we only rely on our hardworking PhD students. is to rely on other more direct sensing modalities and the shared context across direct and indirect sensing modalities to enable the autonomous configuration or association. So for example, the computer vision here as one of the very direct and intuitive modality, it can acquire various information in the less private building regions, for example, just like we show here in the hallway. So if we want to acquire the absolute location of the vibration sensor that's co-located, we can utilize their shared context between the camera and the floor vibration sensor, and as well as the direct interpretable information that we can acquire from the camera to infer it. So for this specific example, the footstep location is a shared context that can be captured by both camera and the vibration sensor on the floor during their sensing task. And here we are going to use a one-dimensional illustration example to explain the intuition. So when a person walks by a sensor, their footstep applied force to the floor and induce a vibration. And intuitively, the energy of this vibration signal captured by the sensor is determined by the distance between the footstep and the sensor. And as a result, if we analyze the signal energy, very simple feature here, indicates a relative location between the footstep and the vibration sensor. And on the other hand, the camera can recognize a person's posture, which is a very mature technology now in the camera's view, and assign the absolute footstep location to the anchor point for each footstep. So by associating this relative location between the sensor, the vibration sensor, and the footstep to the absolute location that the camera sees about the footstep, we can infer the absolute sensor location in the camera view. And this can be done with or without the line of sight between the camera and the vibration sensor. So it sounds like a very intuitive solution, but again, the physical world does not make this association easy for us. Because the structural elements or other factors like a beam or partition of the floor plan, all this would impact the signal propagation model and cause a relative location estimation error. So we will rely on the physical models of the structure, which has been well explored in the mechanical engineering domain already, to ensure that the estimation and the association of the relative location of the sensor and the footstep are accurate. And due to time limit, I'm not going to explain the technical detail here, but long story short, we actually can get up to 7 centimeter sensor location accuracy by taking the physical model of the structure into account. So the takeaway message here is that by leveraging the shared physical context, we were able to associate direct and indirect sensing information to achieve fully autonomous system configuration. And in summary, we utilize this cross-modality shared context modeling to reduce the manual configuration efforts. And along this line, we explored utilizing the detected activity to achieve secure pairing over different sensing modalities to associate wearable device to their location on the body parts and to autonomously configure the vibration sensing sensor location. So now we can easily deploy a system and make the building smarter. Sounds like we're done here. So the physical world is always complicated and impacted by many coupled factors and effects. So if we rely on pure data-driven approach, we're going to need a lot of label data to cover all the different scenarios. So our third challenge here is how to learn better with less or limited label data. Because with limited label data, the pure data-driven approach can hardly capture the real model over different sensing conditions. And the label data is just difficult to get. So let's get back to the problem, the pedestrian identification problem again. As we very briefly mentioned before, each person has their unique walking pattern that's called gait. For example, the two figures on the left-hand side here demonstrate two people with very different gait. The top one walks with his center of gravity linked to the middle, while the bottom one walks with her center of gravity leans back. As a result, their footstep-induced vibration signal are unique to themselves. And we conduct the feature extraction on those detected signals and train a multi-class classifier with it. So let's first look at some results. As shown in the figure on the right-hand side, the x-axis is the number of traces we used for training. By trace, I mean a series of footsteps that's being induced by a person when they walk by a sensor node, like multiple footstep-induced signals. The y-axis is the prediction accuracy of the classifier. So we demonstrate here that both the step level accuracy in the blue solid line and the trace level accuracy in the red solid line. So the step level accuracy is a prediction that's done on each detected footstep signals, while the trace level accuracy, we do a majority vote over individual steps that's been predicted within a continuous walk. So we can see that by using 6 to 7 traces for training, we are already getting like 99% trace level classification accuracy. So that's pretty good, and that's quite doable for system that's being deployed. So then we got a little bit cocky and decided to do a more uncontrolled experiment where we put a cookie jar at the end of the hallway, and without telling people that we are collecting this particular data set for identification, you just go get your cookie. So we call this cookie test, and we got 72% accuracy even at the trace level. So it seems that the cookie breaks our system. Turns out the reason we see a low accuracy is because the people's gait change when they walk when their walking condition changes. And here, this specific condition is a step frequency, or how fast people walk. So here we demonstrate on the left-hand side an example of a person walking at different speed. We can see that when the person walks at a higher footstep frequency, the strike angle of the heel strike is higher than the same person walks at a lower footstep frequency. And in addition, the other parameters such as gait, such as a stride length, also varies when people walk at a different frequency. So then we further look at this, this same person's footstep-induced vibration signal at this different walking speed. We actually see very different waveforms as shown in the figure, where the x-axis is time and y-axis is amplitude normalized by signal energy. So what does it mean for signal processing and learning? Is that when people walk at different speed, the feature of their footstep-induced vibration signal changes. Or in another word, their data distribution changes. So if we train the model, the classifier, with a figure or with a signal from the top figure and test on the signal in the bottom figure, of course, we won't be able to recognize a person because the signal itself is already different. Again, we like simple solutions. A very simple solution is that let's just get data from all the walking speed. This is a quite simple solution that is as simple as asking grandpa to walk in the hallway 1,000 times. Let's change your shoes. Let's change your walker. Let's change different pens. And if you take the medicine, not take the medicine, collect a lot of data. So instead of doing this, what we do is we try to further understand this data distribution change. So we ask one of the pedestrian to walk at 7 different speed, or what we call step frequency here. For each step frequency, we collect 35 steps. Then we put all these collected signals segments together and cluster them based on their waveform similarity. And we end up with 3 major clusters, as you can see here. So we plot the center of each cluster's waveform on the left-hand side, and they are quite distinguishable. We then further look at the distribution of these clusters with a figure on the right-hand side, where the x-axis is a step frequency, walking speed, and the y-axis is a pairing percentage of each cluster. So we can see most of the cluster 1 signal appears when the person walks fast. And cluster 2 occurs more when the person walks more at the medium step frequency. And cluster 3 only occur when the person walks slow. So what happened in the cookie test is that our model is built upon the training data collected in the control experiment, where people walk with most of their medium walking speed. While when we tell the students to get the delicious cookies, they got quite excited and walked faster than their regular walking speed. So we actually test the model with more cluster 1 footstep on the model that's built on mostly cluster 2 footsteps. So another observation here is that the distribution for each cluster is actually changed smoothly over this different walking speed. So let's just keep this observation in mind for now. So of course, we are not the first one trying to handle the data distribution change problem in learning. So let's take a look at this dummy feature space, where the labeled data is marked in the triangle and unlabeled data is marked in the circle with binary classifier problem. So for transductive transfer learning, it'll take into account the unlabeled data's distribution when modeling. So as you can see here, some of the unlabeled data that has slightly off data distribution can still be modeled very accurately. But it does have a limitation that only unlabeled data with distribution that has some similarity with the labeled data can be handled. So now let's get back to our previous observation, where the data distribution changed smoothly with the measurable physical attributes, the footstep frequency. What does it mean here for us is that the footstep frequency now that can be measured, it's a measurable attribute, and we can actually use it to tell whether the transductive transfer learning works for these data points. So given the labeled data and their measurable attributes, we know this part of the unlabeled data can be accurately predicted. So with that, we propose the iterative learning that's been guided by these physical attributes, where we first understand or discover the relation between the directly measurable physical attributes and the data distribution, the change of the data distribution as described in the previous slides. Then we handle the similar data distribution change in each iteration, as shown on the figure on the right-hand side. At the end of the iteration, we can expand the model by just providing the pseudo label on the new prediction. Then by the next iteration, the data distribution that can be covered is expanded as well. So on and so forth. Eventually we'll be able to cover the larger data distribution change with the help of the physical attributes learning. So the key here, the key of to ensure the accuracy here is to use physical attributes to control the iterative learning order so that in each iteration, the pseudo label has a higher accuracy. So getting back to our pedestrian identification problem, where we test our iterative learning algorithm on 10 people's walking at 7 different walking speed data. And we only provide label data at a medium walking step frequency. And we test all the walking speed. So we use the conditional supervised learning SVM as a baseline, where we can see when the step frequency is extremely different from the label data, it achieves really low accuracy. Since we're identifying 10 people, when people walk slow, the accuracy is almost 10% is almost random guess. And our iterative learning, which propagates the model in the order, it achieves an up to 3 times improvement on the extreme distribution change, and an overall 1.5 times improvement for the all step frequency data. So the takeaway message here is that by leveraging the physical knowledge measured from the sensing data, we were able to characterize the domain shift and adapt the learning model to achieve better performance. And in summary, we conducted adaptation to the learning model with physical knowledge to reduce the initial label data that's needed. We have a few work on this direction, including physics-guided transfer learning that handles structural variation, semi-supervised learning that utilizes physical knowledge on information granularity to achieve cross-granularity learning. And we also have some localization algorithm guided by the physics model so that it can handle the varying velocity, wave propagation velocity changes. So in conclusion, from the system perspective, we achieve less sensor, using less sensor and less configuration efforts by characterizing the deployment's physical property to optimize the system performance, and using cross-modal physical context modeling to reduce the configuration efforts. And from the data perspective, we characterize the data distribution change and its physical costs to reduce the initial label data that's needed to get the accurate estimation. So that will be the end of this talk. Thank you, everyone. Please let me know if you have any questions.
Thank you, Professor Pan, for a fascinating talk. It's really exciting work to see. There are a number of questions coming in through our Q&A forum. And so we'll start with our first one. IO expresses a lot of excitement about the results and wants to know, were the sensors built in-house or were they purchased?
Right. So for the, let me get back to the video. So if you can see here, the sensor itself, particularly for the floor vibration monitoring, is this exact cylinder that's called geophone. So we are using this geophone, which was used by our civil engineering friends who measures the earthquake. We repurpose that to measure the human-induced vibration. And we, for the on-body monitoring and the other applications, it depends on the application, but we do build our own sensor sometimes too.
Great, thank you. There's been some interesting questions focused on questions around objects like wheelchairs, and then a larger issue of the maybe potential socioeconomic bias causing sensing unfairness. So have you thought about that, and what does this mean in your research and how you plan to address it?
I see. So for example, for wheelchair, just like other activities, when you use a wheelchair, it also creates vibration. And the difference is that the wheelchair induced a vibration and a human footstep, like stepping on the floor, actually have very different excitation, and they might cause different type of vibration. So we still be able to detect the activity if a person is using wheelchair, and we actually have some of our work on talking about the friction-induced vibration versus impulse-induced vibration that potentially can be the solution to this problem. And in terms of the socioeconomics bias, say when people purchasing different type of sensors, whether they can achieve the same level of accuracy, and if not, how can we improve the, say, cheap sensors accuracy by by the knowledge we can gain from, say, a more direct sensing modality or a more accurate sensor. So that is an ongoing direction we are exploring right now.
Fantastic. Professor Du has two questions. The first is on sensor placement. Is the goal of sensor placement to place the sensors as close as possible to the feet of users?
Oh, that's a great question. So it's actually a trade-off, right? So just like you see here, the cylinder sensor, you don't want to put it in the middle of the hallway, even that's the best, that gives you the best signal strength, right? Because that bothers user, or it could be a tripping hazard. So what will be the optimal sensor placement for a particular household or for a particular group of people? That's actually a great question that we should look into. What's the trade-off between the convenience of the user versus the quality of the signal that you can acquire so that you can get good accuracy? So that's a fantastic direction that I would love to explore.
And so then a follow-up question to that is, many users may have similar daily moving patterns. So could you learn the locations of where users step their feet the most within your experiment, or incorporate other physical knowledge?
Definitely. So we also have some more step level localization where we use multiple vibration sensors to localize where in a two-dimension space where the first step occurred. So that can provide the insight on where the people step the most, for sure.
We've also had a couple of questions come in about the calibration phase of the sensors. Can you describe the process of calibrating and determining the sensor placement a little in more detail?
So when you say calibrating the sensor placement, are you talking about like what will be like what exactly are you looking for? I'm not 100% sure, but let me explain what the system needs here, see whether that answers the question. So a lot of things in our structure would impact the signal acquisition. So for example, if you accidentally place your sensor on a beam, then it might not, the beam itself might not vibrate a lot, or your building have certain damping mechanism that just reduce the amount of vibration human can induce. So when that happens, you might want to use a different hardware configuration so that it can have like it can acquire a better signal to noise ratio, or you want to put the sensor to avoid a particular structural elements that will alter the propagation of the signal. So by that, sometimes we call that a calibration for this particular system. For example, what we show here, that the student is knocking on the floor to generate a knowing signal that propagates to the sensor, and we can understand how good, how bad the system capturing this particular vibration, and whether whether we want to move the sensor to a better place. This is a current approach that we would call calibration for the sensor deployment at this stage. Yeah. But if you are talking about the sensor itself, the calibration could mean that when the sensor is manufactured, whether it fits the description of the frequency response for the particular vibration signal, that's a different type of calibration, but that will be done by the manufacturer. When we build our own sensor for other applications, such as our teeth monitoring, we actually also need to do that, the calibrate, so that the sensor we can ensure that sensor will capture the same characteristic of the signal like for the same excitation.
And then a follow-up question to that related to calibration from IO is, once the calibration is completed, do all of the calibrating sensors need to remain, or can you reduce your sensor complexity or the sensor network complexity once you've learned patterns?
Oh, that's actually a great design choice. So it really is a trade-off between how dynamic is your environment versus your sensor sensor deployment, right? So imagine, say, a different type of loads could potentially impact your signal. Say furniture is a type of static loads, while the human ourselves is also a type of more like dynamic loads. So if you see a lot of traffic or a lot of changes in the environment, then this calibration, automatic calibration, is necessary over time. But if you are looking at a more static, like once you put it, you're not moving it for a while. Eventually, like at least before you change the system deployment again, you don't need to do too much calibration. Just like think of the Amazon Echo at home. Sometimes you do move it, but once you move it, you might leave it for a while, right? So every time the system deployment changes, characterization or calibration might be necessary.
Fantastic, an interesting design problem for sure. Maybe we have time for one last question from Andres Albanese. He's asking, can phase array technology be used to track the user and get a better signal?
So when you say phase array, what exactly you're talking? Are you talking about the RF-based sensing that you use either like you use a radio frequency to sense people? Sorry, I didn't quite get the question.
Yeah, I think so. So typically, these are electronically scanned arrays. So if you have different beams of, say, radio waves, for example, to see if you can enhance the signal.
Definitely. There's tons of research on using, say, just home Wi-Fi to sense people, right? So we do compare ourselves with different sensing modalities, and every sensing modality has its own pros and cons. So for the particular modality, such as Wi-Fi or millimeter wave-based method, like comparing to them, the advantages and disadvantages include, for them, they might just use existing, say, infrastructure that to conduct the sensing, but for the same thing is that they might be limited by the resolution of information that can acquire. So for example, if I just move my pinky finger, or I typed, like I just type a little bit on the table, it may or may not be able to be detected due to the dynamic of the environment, or a multipass situation, or just a noise in the environment. The advantage of the vibration sensing is that by looking at this as a whole modality, you can extract a different resolution of information, as well as different scale, say from house level to on-body level, to say just I tap my teeth and I'll be able to know, say, whether I have a fitting issue, or if I say something without making a sound, that like the vibration caused by your cheek wave would be able to allow us to understand the unvoiced speech. So this gives us a more fine-grained activity monitoring. And for example, you're cooking today, but your motion, when you stir fry, your motion has a different trend, hence say causing the vibration signal is having different features that will allow us to further conduct the behavior monitoring. So and like in overall, there are always pros and cons, right? So what we eventually expecting is there's not going to be one modality that can solve all the problem, and being able to find their complementary to each other, on body, off body, RF, vibration, light, whatever, camera too, will be the ultimate goal that we are seeking for.
Thank you, Dr. Pan, for sharing with us your very exciting research, and we're looking forward to what comes next out of your lab. If you'd like to connect today with today's speakers, we've posted a link to her webpage in the chat. That's at www.pans-lab.com. Thank you, everyone, for tuning in today. Please join us again on Wednesday, September 29th from 12 to 1 for a talk by Shara Tibkin, Managing Editor of CNET News, for a discussion on digital redlining, the broadband gap's dirty secret. The Research Exchange webinar recordings can be found on our YouTube channel, and today's talk will be available for viewing by tomorrow afternoon at our YouTube channel at Citrus UC. Thank you, everyone, and thank you again, Dr. Pan.
Thank you. I'm very excited to be here. Bye.